All right, everyone. Welcome to the second week of Kangaroo. Now, the module for this week, even though it says Kangaroo 2, it's actually just an extension of the original Kangaroo plugin. Although at the end, I've provided links to install the Kangaroo 2 newer version that was just released, and you can mess around with that if you're interested and try out some of the stuff. Now, going back to this in particular this week, we're going to move on from looking at the catenary simulations to minimal surfaces, and a total of 5 examples that are somewhat all kind of related. The first 3 will be using Rhino geometry to create the point networks that Kangaroo can simulate with, and 4 and 5 actually use mesh geometry. That you'll see there's a bit of trade-off between these 2 versions, where the mesh geometry, while the initial setup might be a bit more difficult, you are able to kind of get control over certain boundaries and individual anchor points by using a specific technique, whereas the Rhino geometry version is much easier to kind of deal with initially, because you can just give it polysurfaces or curves or lines, that sort of thing. Okay. So this week's file is this Kangaroo minimal surface base, and as before, it will look like this with your inputs basically on the different layers. So you just have to open the corresponding file or layer that you're looking at to be able to get the inputs. So in this case, you'll see that we have, for the first one, we have 4 points. So we'll have 4 points, and we'll use those as the inputs. Just copy drag it 4 times. And a shortcut I use is select them all, use this align to align them, and then the one on the top to distribute them vertically. Okay, so that's our inputs, and you can go in and click these basically one by one. And I generally try to kind of do this in clockwise or counterclockwise, keeping that consistent as to try not to cross over, because that'll introduce weird things. Okay. All right. Well, we're going to try to make a surface out of these 4 points. So if you type surface, there's a 4-point surface, exactly the same as the one in Rhino. Oops. So you would do that. The 4-point surface. And you'll see it's actually a hyperbolic paraboloid. Okay, so let's try to divide this surface. Actually, just divide surface here. So this is the surface divide. We can push this in. Let's do a number slider, goes from 0 to 30. Let's set it at 15. And push 1 to the U, Alt drag, and get 1 for the V. Okay, so that's our basically what we have now is a series of points that lie on that surface. Now we want to, if you kind of remember the Kangaroo inputs, and let's go to the Kangaroo panel. The original physics solver. And in this case, still we're using the springs from line component. And the springs from line component obviously needs a connection that is basically a short line segment, tells that what is the length or what are the 2 points that the spring acts between, right? So we actually will need all of these sort of little line segments that are in between each of these points. And so first off, you can try basically using a polyline and use these points, the division points, push those into the vertices, and you'll see immediately, as I kind of hide all of these inputs, you'll see immediately it only draws in one specific direction, right? This is going in that direction. And I need the ones that are going in the other direction as well. So if you look at this, and this is because, you know, the numbering scheme of the points are going this way or that way. Basically, they're going one direction, which you can see by taking a look at the data structure as well. So each of these is one list of 15 or 16 points, 0 to 15. So the easiest way to deal with this is by using the flip matrix component. By flip a matrix like data tree by swapping rows and columns. So what happens, and you'll see, if I take those points and flip the matrix, copy the p-line over, is this will actually give us all the lines in the other direction. Right? So now you have a grid that lies on that surface. Okay, simple enough. Now, what we want to do is we actually need each of these individual line segments broken down, because those are really the springs. Right now, these are all long p-line segments. So we can simply just explode them all. Hold down Shift, push that in. So both of those inputs go in. And remember that these, right now, are still actually kind of sorted in some sort of data structure. And that Kangaroo does not like it when you have a data structure like this. So we will actually have to flatten these guys into one long list of lines. It doesn't like hierarchy, and push that into the connection for the springs. Now, the rest length, in this case, we would just leave as 0, which it is right now, because compared to the catenary arch or catenary curves, there is a rest length for those elements of it. In this case, it wants to basically shrink as much as possible. So the rest length is 0, and there's basically simulating each of these line segments as a very tight rubber band or a spring. The catenary kind of works in reverse, where there is kind of a minimum length, and you're letting it extend. So that's the difference. So in this case, we don't actually need this input, the rest length input. Okay, so this goes into force objects. Now, because this is the only force object here, in this case, you actually don't need the flatten, because it's already flattened coming out of here as well. So the next thing is anchor points. Anchor points, basically these 4. Now you could essentially flatten it first, and then basically drag all of these anchor points into here individually, which are the 4 points at the corners. But that's a little bit messy, so we'll use the merge component to, and you'll see it automatically adds more as you go, and then you can zoom in and delete one of those inputs. Okay, so what this does is it merges the 4 points into a list, and that goes into your anchor points. That settings, we can skip geometry. Now geometry, actually you can pull from multiple places, because you're basically working with with the translation vectors, or basically the movement of each of these points. So in that sense, it could be these vertices, but I think what's easier actually in this case is this, which is its original sort of division points. And so you go from here to there. We need a Boolean toggle and a timer. Right click, set interval to 20. All right, so that's more or less it. I'm gonna hide Control Q to hide most of the unnecessary stuff. Activate this, and all right. So you'll see these points are basically drawn together as if they're small, short springs in between each other, but anchored at our 4 anchor points. And this would basically be very similar to the point distribution on, let's say, a piece of pantyhose. Okay, our geometry out on this end, we will actually do something very similar to what we did here. Now, let me pause that, because these are basically the reason that that works really well for us is that these points are actually done and sorted in the order, right? Even though, you know, the simulation is kind of working on them in a sort of flattened state, but because the points are still related to their original organization, the geometry out will retain that data tree organization. So that's kind of great for us, because then we can use this geometry out, and you'll see, let's say if I try to draw a polyline using those vectors or using those vertices, you'll see the polylines actually draw in the same structure as it did before. Now the problem with the polyline is that it has kinks and it curves and it basically bends, you know, between straight lines, so we don't like that so much. So instead of polylines, we are going to use, let's go to curve, spline. We're going to use the interpolate curve. So this will actually draw lines through with a smooth curve transition. It's the exact same one as the one you find in the base Rhino command. Okay, and so we can take these. You could try to loft between all these, but nothing would happen simply because your data structure right now is one curve in each list. It doesn't know what you're going to do. You're doing a loft with one curve, right? And so as you might imagine, we would need to flatten this tree down into the loft. And in the end, if I hide all this, you would get a minimal surface that's anchored at these 4 points. We can bake it. And to see, that's what you would get. And this would be very close to, let's say I had a uniform tensile fabric like pantyhose, given that it stretches in both directions uniformly. Okay, so that's the first example. The second example we can easily modify off of this, and so I'm going to disable the simulation, go back. So the second example, you'll see we have basically 2 input curves, right? So obviously we'll need a curve component, curve container, and I'm going to delete this and this and this. Okay. So set multiple, set multiple, so pick 1 and 2. Both of these come in. And we're actually just going to loft it because it comes in a sequence. Kangaroo or Rhino knows that you're trying to loft the 2 curves in the same list. And then this actually loft is what we're going to give the surface divide. Now, the surface divide, if you open the preview, you'll see that we have a problem because you're getting like really, really long rectangles, right? So you actually want to balance that out by, in this case, upping the V count, so you get a more, you know, reasonable sort of aspect ratio. Now this actually will affect your result to a great degree, but basically, the more of these points you have, vertices on each, let's say, sort of tier row you have, the looser, right? The more that part is able to flex. So the sort of point count actually does make a difference in the final simulation to a certain degree. All of this is actually more or less the same. You'll see that the same principles apply. Like, so these are the sort of horizontal lines. We flip the matrix to get the vertical lines, and to be able to get this wireframe network that works for us. I'll hide that. Okay, So this is what we have more or less at this point. Now, the big difference here is really in our anchor points, because what we want, originally our camperds were just those 4 points floating around. With this, because our inputs are this sort of whole ring around it, our anchor points are like basically all of the points on the top and all the points on the bottom, right? So one relatively, I guess, easy way to kind of get to that stuff is actually to list item. Simply because these, let me see, these lines, the vertical ones, the anchorage points are basically the first one on that row and the last one, right? So simply by using a list item, this, we are able to, let's see, it's these guys, right? Okay, so if you do that, and 0, 1, oh, sorry, actually we should be looking at the points here. So the flipped ones, right? So this should actually go there. And you'll see basically that's the sort of first top row of points that we're wanting to get. Now to get the bottom row, I'm going to copy this again. And you can either basically draw from like this, which is the U count, into the I. Now the I is the index, right? This is 0 by default. If you want to make it more explicit, you can actually just type 0 in. Sometimes that helps for the readability of the definition. And this is the last one, right? Which is actually coming from the U count, essentially. This is how many divisions you have. Now, there is a way, let's say for some reason this isn't apparently obvious in your definition. What you can do is to use a list length component to measure how long this flip list, sort of how many points are in there. And so if you look at this, essentially there's what, 16 in each list, right? Now 16 in each list means that there are essentially 16 items going from 0, 1, 2, blah, blah, all the way up to 15, right? So 16 items means you would have to, for this to work correctly, you would have to do some math. Take that in, oops, take that in, copy paste this, and make that 1, right? So the answer you get in the end would be 15. And you push that in, that would work as well. Okay? Now, this is the explicit way of doing it. The sort of quicker, neater way of doing this is actually right-clicking on the input and using an expression, an x minus 1. So that's a variable, which is the input variable minus 1. And that does basically the same thing. In this case, because we're letting the index wrap around to the end, basically 0 minus 1 is -1 to wrap on to the other end, and that actually works in this case because we have the wrap index set to true. Or you can just put the length in, and it basically should give you the same thing. So this is actually a really good example of how, you know, list item is one sort of really one of the useful components you can have here in Grasshopper. Okay? Alright, so these are all our anchor points. These are our anchor points. So what you can do is actually just go that anchor points, hold down the shift, put that into anchor points. You'll see Grasshopper, it will not like it very much because your anchor points, your loft here will fail because your anchor points are not flattened, right? So remember, Kangaroo likes your inputs to be flattened, and then the loft will succeed. Okay? So that all this stuff is actually more or less the same. I'll unhide that, turn on the timer, and run the simulation. Okay, and we can hide all this stuff. Just get it out of the way. And I will pause the simulation. So that you have basically a tensile fabric stretched between two hoops. Bake it, say OK. And that's what that would look like. Fairly close, it would be very, very close simulation of a real similar material. Okay? All right, now let's move on to the third one. Now the third one, number 3, minimal surface from polysurface. Now this is going to be a completely different approach. So actually most of this is going to not be used. I'll turn off the simulation. Okay, so you see here I have a polysurface. Note that it's an open polysurface. These basically only work if you have like open ends, right? So to anchor to, if you think about it. So this is a B-rep, and obviously we need a B-rep component. And let's reference it in. I'm going to hide the geometry. And for this, let's actually mesh the B-rep. We'll mesh the B-rep, hide it again, just kind of get it out of the way. And so the mesh is like this. Some of you might have to set your display to preview the mesh edges. Otherwise, you know, any sort of mesh subdivisions will not show up. So make sure you kind of activate that so you get the lines on the edges and you're able to kind of see mesh sort of facets in your Grasshopper display settings. And we are going to use, basically go to the mesh panel, under utilities, you know, remember you have the quality settings, etc., etc. We're going to grab the custom settings from here. And let's hook that in. Now, the main reason I want this is basically, as you can see, as soon as I hook it in, it actually subdivides this into smaller portions now. And what I want to constrain here as a fixed number is these two, the minimum and maximum edge lengths, to make them the same. And you'll see, let's do 0.3.00. This basically controls the sort of minimum and maximum edge length. And if you have hooked them all together, that basically forces your mesh subdivisions to be a certain size, right? So you can make this, basically make this mesh as dense as you want to. And remember, like I said, the denser your sort of mesh is, you know, the looser or the sort of springier the Kangaroo simulation is. For now, let's just set this to 0. So we can work with it. All right. So this is actually a really easy way of controlling more explicitly the density and quality of your mesh. What's common in these is that because the polysurfaces were meshed in a way separately, that this is actually not a fully joined mesh. And so you'll have problems working with it. And therefore, Weaverbird has a tool here. Weaverbirds join meshes and weld. So returns a single mesh object. And you'll see, let's see here, where originally that. And let's try this. And you want to set this to join, set it to true. So Boolean toggle here and set that to true. So you'll see if I push in a panel here before and after the join, you'll see it has the same amount of faces, but the vertices have been reduced, right? So this join component basically, let's say, merges the vertices that are coincident with each other. The vertices that overlap basically are merged into the same, right? So here you would actually have 3 vertices originally, and they all basically get merged into the same one. And that forces the mesh to be joined together. Let's triangulate this further once, like that. Okay. All right. Let's go back to this, and actually we don't need any of this anymore. Let's go back to the Kangaroo and take a look. We can hide some of this stuff as we go. Here, let's see. We need our force objects, right? So the springs are one big part, and remember, once you have a mesh, Weaverbird again has the Weaverbird edges, mesh edges component, which helps us grab, if you give it the mesh, helps us grab essentially the mesh network, right? The wireframe network of the mesh. So these basically are, as before, the connection. You don't need the rest length in all the minimal surface sort of examples. All right? Anchor points. Our anchor points are the same things, you know, the boundaries of the mesh, outer boundaries, right? So it's the same thing if we kind of find, again, our naked edges. So same thing. And you can just like type it. This is just easier. Naked vertices, the NV, like in the example we had before, and just pull these from here. I have to move all these back a little. Okay. Easier. All right. So we want to grab all of the naked points as the anchors. And if you need to visualize these, just pull in a point collection and grab it in, hide this, so you can see, okay, yeah, these are all the naked edges, right? Okay. And that goes into the anchor points. And you don't need to flatten this here because there's only one input, at least in this case. Our geometry, again, comes from, in this case, actually, we can input the mesh itself, the mesh with the triangle faces. All right. And then as an output, we'll use a mesh container as well, and the geometry as well. So turn this on. Let me hide this. These are basically your anchor points, the whole row on the outside. Those are your edge meshes. Let me delete that, so that's out of the way. Okay, so you see that that holds basically the edge lines, and that's the mesh output you would get. And you'll see this is one characteristic that instead of, in the input geometry, instead of working with points or vertices, in this case, Weaverbird is able to work with the mesh geometry directly. And you'll see that I can make it that higher, and you'll have to reset. But you'll see that, okay, it's not as accurate. You get more facets. Now, if I move it down a lot more, and then it'll get a lot heavier, so kind of be careful with that. It'll take longer to converge or basically reach equilibrium, but you'll have a much more denser mesh network with a much smoother, curvier surface. you can pause that. Take the mesh and bake it. All right. And that's what you get basically from a very simple, as you remember from before, a very simple polysurface input. Okay, that's how you get that. A lot of the work is really in getting the right polysurface configuration. Be careful with this setting. Don't go too small. It will most likely freak out. Okay, that's it for the first three.